Good afternoon, ladies and gentlemen. I hope you can all hear me. My name's Tommy White, and I'm one of the developers of the MasterSeries. Today's webinar is on connection design to EuroCode 3. We have had connection design out for the last 26 years, and it's gone through a lot of different transformations between the BS and then the 1990 edition of BS, the 2000 edition, and now the EuroCode. Our EuroCode connection design has been out for the last year and a half and has been very widely received. As you're all probably aware, it is one of the leading connection design software packages around the world and is used by most big fabricators and consultants. Today, we're going to look at what the software can do. We're going to look at the different types of joints we can handle, and we're then going to look at doing some connections and the difference between the EuroCode and the BS edition. So I'm just going to minimize this or turn off this little welcome page, and I'm just going to go into my software page. Just as a wee recap for everybody, we at MasterSeries design a lot of different software, a lot of different materials in buildings. We have our building design suite, we have our analysis for multi-story frames and trusses, concrete, and as we're looking at today, connections inside the steel group. We also do composite, timber, masonry, retaining walls. If you want to try any of these pieces of software, just go onto the website and request a 30-day trial on the software. So if I was to go into my connection design web page, I would see a nice video on the connections, but I would also then see an invite to today's session and a free trial request form. So hit the request form, fill in your details, and off you go, requesting a 30-day no obligation trial on the software. So let's get into our connections. What can we do? Well, if I just go backwards here a second, there is a nice little link at the bottom of this page on what types of connections can we consider. So if we look at our little PDF, we can do eaves, beam, column connections, either haunched or unhaunched, stiffened, valley beams, apexes, base plates stiffened or unstiffened, beam splice connections, column splices and hollow section splices, and then we move into the simple connections, or not so simple these days, for flexible end plate and fin plate and even angle cleat connections to both beam to beam and beam to column. So I'll just close that down, and if you want at any stage we look at that document, it's there on the bottom of the web page. So let's start the MasterSeries. Here it is, and we'll go into our element design and connections. So let's look at the connection I was looking at earlier today and open this file, and let's just walk through some of the different connections that we have in this system. So this is the interface. Very straightforward and very simple. We will get to doing some real design in a moment, but just first of all I want to do a more detailed review of the types of connections we can design. So if I just drag this down a wee bit, because we're not interested in the results at the minute, and we can see our very standard, very simple beam to column, or as we call it, eaves connection. Beam to column flange with some bolts. We can also then go for the haunched connection, and then we can go on and move through to the stiffened haunched connections, and you will notice in this example we're even able to put double bolts above the flange to give us that additional strength up there that we wouldn't have had otherwise. And we have a Morris stiffener and a compression stiffener. If we then move forward, we then see a valley connection, but this isn't quite a valley. In this case it's a eaves with a little cantilever coming off the side. I did it that way because it's more interesting, as we will see when we start to talk about the design. So moving on, we then come into our unhinged multi-story rigid connection. Still an Eaves type connection, still that one joint type. And now we move into our apexes, or sort of a end-plated beam splice, and then into the base plates, slab base plate, and the more complicated stiffened base plates. The stiffened base plates, we can do 9 different configurations of stiffeners, which can get quite scary. You'll notice that we're always using the effective area method where possible. We are working to the EuroCode. It says EC3 with the UK National Application Document. So being confirmed all the time. Our stiffened one we saw. Beam splice. The cover plates beam splice. In this example, we have inner plates on the bottom and outer plates on the top, and the bottom plates are with countersunk bolts through onto the flange. That has a design penalty, which is considered, but gives us a nice smooth flat finish to the bottom of the joint. And then we have here, we have staggered bolts with inner and outer plates on a connection. Now, not all of these are designed. They are here to show you what we can do. Some of them go a wee bit far for the fun of it. Our column splice, non-bearing, with cover plates, very simple, very straightforward. And then we have the bearing with a division plate, and we can see that we're confirming that our spread is coming through. We have a smaller section above, so we have a packer plate, and we are checking these again, countersunk bolts for that long joint. We're doing all those checks to make sure that our weakened bolts are satisfactory. And then we come into this hollow splice, and there is the rectangular and the circular hollow splice. And then finally into the simple connections. Now this one looks weird, but what we have is a horrendous 1300 deep section. It's a plate girder built up with a 200 by 15 top and bottom flange and a 170 by 10 web. So in fact the overall depth is 170 plus 30, which is a 1200 deep plate girder. So we can on the fly very simply define a plate girder. Not very simple, we can just come in and say, rather than using a UB or an RSJ or even an IP, DN or a W, any of these sections, we use the built up section. And we specify our dimensions. Again, we have all those grades. And we nowadays have all the steel sections in the database for all the British, the European, the American. I think we also cover the Chinese sections as well, and the South African. And with the 2015 version, they be segregated into different groups, so everybody doesn't have to see everybody else's sections. So I'm just going to close that. We're still just walking through the types of joints. A more simplistic beam to beam simple connection, in this case with fin plates, and the right hand fin plate needs that extra bolt. Rather than having 4, we need 5, so we went for a staggered pattern and just reduced the spacing slightly. We get a joint that works for this shorter height. As you can see, 1, 2, 3, 4, 5 on the left, and we have 5 on the right, which would not fit if we stuck to a single line of bolts. All our simple connections also work on tie forces. If we don't define any, they will be assumed. In this case, I have no forces defined, so if I put in 200 or 400, 400 getting a failure, and we're getting some failures on different criteria. So we'll be looking at this in a moment of how the failure symbols are worked, how the design is worked, and then a similar connection, in this case, angle cleats. Now, the EuroCode, the SCI Green Book does not cover angle cleats because it feels that they're out of date and old-fashioned. But I know quite a few large fabricators that still like the angle cleats because they do not require welding. They are very quick and efficient to produce, So we have introduced, using the rules, angle design as well for you. And then finally, we'll move into the same onto columns. And this is a 203 with some beams coming into the sides. And if we then look at the web beams, we will see that again we have 152s. Now, just to show you the flexibility of this program, if we look at the column, we'll see that that meets in without a problem. If I was to come back to my beams and I was to take this beam, I was to make it not a 152, but just move up to the 191 and apply, we would see these little notch lines occurring here, because what's happening is that we're looking at the geometry section and saying, no, we need to notch this beam to get it in here. So if it's notched, we will, in our calcs down here, we will actually show it up as hanging design. Now I'm just going to expand and modify my display so I can now see as I scroll up and down, if I put some loads onto this beam of 200, because we were only looking at geometry at this stage, you will see we also do our notching checks on our beam, end plate shear, block shear, local resistance of the member. In here somewhere we will find there is a check on the supporting member for the notched capacity of the section. So moving on, there's only probably two left. We have the same with a flexible end plate, and then just for completeness, the angle cleats. And again, when it's drawing them all, it can be a bit crowded, but really when you move from zone to zone inside the editor, it shows you only what's important at that time. So let's get back and first of all do ourselves a design. So I'm going to add in a joint, and I'm going to add in an eaves joint. So now we're going to do a simple design, and I'm going to make it type 1 because I just prefer the rafter on the right hand side. I don't know, it's just my preference. So first of all, we'll put some moment in, 450, we'll put a shear of 200 and an axial of 185.6. That's fine. And put a moment at the end of the hunch, and that is very useful because that allows us to design the end of the hunch accurately if we have a hunch. And of course we're going to have a hunch. So 900 overall depth, here my geometry comes in, and I'm going to say my overall hunch length is 2.1 meters, and I have a slope degree angle of 6 degrees. So basic geometry set. Let's have a look at the different areas of this design, and then we'll look through some of the details on it after we've designed it. This is the graphics and this is the input. Those are easy. This is all my results. That's easy. What we also have here are some blue background here, and that tells me that there is a dimensional problem, and that dimensional problem is that taking into consideration the bolts here, we may not get a good fit in of our bolts. So if I just go and zoom in to here, you'll see that the bolt length is just saying we may have a problem. And in this case, it probably isn't a problem that's quite close up, but if I come along in the bolts and I move that from 90 to 100, or sorry, from 80 to 90, it now does not show any blue. So we've got some compliance. Geometrically, it can be manufactured. But I've also still got some little red dots here, and I've got a blue background. Well, the blue background on the results means that the joint isn't working, it is failing. In our case, it's a 2.15 unity, or 115% overstressed. Obviously, we need to put something more in, and the red dot's telling us the bolt is failing, give me more bolts. So coming in very quickly, another row at 90, we've got down to 68% overstressed. At this point in time, the bolts are no longer restricting the capacity of a joint, because in the EuroCode and even in the BS to the Green Book, we're dealing with calculating the capacity of a joint and comparing that against the applied load. So we need a stiffener. base plates, plates, bottom stiffener, 12 mil. So we've come down to 26% overstressed, and again now the bolts are the critical component. So back to bolts, a third row in, and the joint now works. Now, by default, and I noticed from the comments already that there are problems with end welds. Yes, that is one of the things you're going to see in the EuroCode, is that the end of haunch welds are quite problematic. And one of the ways to reduce that is to go and put in the haunch, end of haunch moment, and that will help reduce that weld. This is just the default, which is 0.7 of the thickness, or full depth actually in the end of that. And these are a bit high, so I'm going to come back and rationalize my welds. So coming down, I'm going to say flange top weld with a 6.2, maybe prefer an 8 because it's a very principal weld. The bottom flange, a 6 will do fine, and for the webs we'll put a 6 in as well. End of haunch, we're going to go for a 6, and it fails, and a 6 down web. So we need more than a 6, but it's not failing by that much. It's failing by 30%, so 6, maybe 8 might work. 8 works with an 8 mil end weld. Now, if I was to come back up and take out this value, it's going to use the full moment and cause us grief. So in fact, 250, the reduced moment as it drops down to the end of the haunch, super. That is all that's required. So that is how quick it is to size a joint. Obviously joints don't have just one loading case, so I'm going to put in a reversal case, and I'm going to put in a negative load of 355, a shear negative of 200, an axial in tension, which is detrimental, of 175. So I've now got 67% overstressing and 2% on the flange welds, because I put that weaker weld down there. So what do I want to do? I want to come along and solve the first problem. I can see I need a stiffener up here. So back to the plates, stiffener, top row stiffener, put a 10 mil stiffener in there, and we now need more bolts. Not up there, but down here. Get some more bolts with good lever arms at 90 up, and another 90. So we're now got our joint working. However, we need to be careful, because having added in that additional set of stiffening and bolts, we may have caused a problem up here by reducing some of the values. So it's very worthwhile coming back and checking. So if I was to play around with this just for the fun of it and make that 750 so it fails, but I go to my loading case 2 and it works, happy days. How do I know? Well, I can scroll through the cases. Now in a standalone joint like this, we can have 10 or 15 cases. In a integrated connection with a frame, we could have 30 or 40 or 50 or 100 ultimate cases in some instances. So we have these little fails. So it'll say for the next joint, or for the current joint, move through the cases and stop when I get a failure. So yes, that was failing, and we would have had to take action. So that's holding my hand. So now let's look at what has been designed. So what are the real differences? Well, really, when we're looking at this Eaves connection, which is one of the principal connections in the Green Book on connections to EuroCode, we will see that we actually have modes that are different for PL1 and PL2, for effective length 1 and effective length 2. And the reason for that is that we use, and I'm just going to pop up my publication and come on down to the right page, and yes, this is a legitimate registered copy. We will see that we actually have what we call circular patterns and non-circular patterns. That's similar to before, but what has changed is that we only use the circular pattern for mode 1 failure. For mode 2 failure, we use only the non-circular patterns. So it's distinguishing between full yielding and the prying plus yielding loading cases, or not loading design cases. So to the EuroCode, we have to work with these separately, and if we look at our results, we will see that we are getting LEF circular patterns is 343, LEF non-circular patterns is 301. So we are checking slightly differently. The other modification really to the EuroCode version is that when we're looking at the mode 1 failures, we're also modifying the resistance to take account of the bolt head and the washer at the yield locations. Now, when we come into looking at bolt row 2, then we need to look at the bolt row 2 and, as before, bolt rows 1 and 2 together. So that's very, very similar to what we did before, where you take in not just the individual bolt row, but the combined bolt rows, where you will see here we're talking about the configuration for the first row and second row. You add them together and you go forward from that, and you do this as you move down through the joint. So for the bolt row 3 here, we will look at bolt rows. Yes, the calculations are beginning to get quite long. We will look at bolt row 3 on its own, and then we'll look at 3 and 2, and then we'll look at 1, 2 and 3, and in each of those cases we will work out the resistance. So for the column flange and the end plate, those changes are significant but not that different. The big difference is when we move into the column and beam webs. In the column and beam webs, we have this beta value. So if we look, back up to our calcs at row 1, easiest, let's not look at too many calcs at first. We have in the column web tension, we have an omega value and a beta value. And the omega value can frequently be less than 1. 0.7 is actually a typical value. In this case, it's 0.88. And this reduces the capacity of the web. And the omega is, I think, really based on the difference between the moments on either sides of connections. So on double-sided connections, it has an effect. The other difference between the two methods, the BS and the EuroCode, is the effective length. Previously in the BS, we took the distance from the bolt edge, spread out at 60 degrees, and we got a length of web in tension. Well, for some reason in the EuroCode, they say no. We now use an effective length is the same as the effective length of the bolts in yield LEF. So that's actually giving us higher capacities, and that's going to give us a higher capacity even though we've actually had a reduction due to omega. So it's swings and roundabouts, but in the end we get a bigger capacity because of these omega and beta values. So those are all designed and calculated, and then all these tension forces that we've derived are compared against the capacities in the compression zone. But before we do that, there's also an additional plastic distribution check. Now there's a third distribution check required in the EuroCode compared to the BS, and that can actually result in a particular row of bolts suddenly being allowed to go plastic or not plastic, which was different from we had. And if I just pull my force diagram in here, it should be, here it is, here it comes. In this case, we are pretty inside the elastic line, except for these rows, which are probably not going to be considered anyway as part of the ultimate design, but these would be allowed to go plastic, whereas these are being limited by their proximity to other rows. But they all have to be balanced against the column in compression. The compression of the rafter, the compression of the web, all these. So the beam compression and the column web compression need to be considered. And there's another modification factor involved here. We have our old friend omega, which is coming in, and there's also a K factor that comes in to the design of the buckling. And again, it's to do with what we call coexistent compression. So if this was a multi-story member, previously the BS, we weren't interested in what the axial load here was and how it would affect the compression capacity or the shear capacity of the section. Now we are. So if I was to say there is a column axial load of 200 coming from above, it can actually suddenly start to modify my capacities. Obviously it's very insignificant. If I put this up to say 500 or 1500, now we're beginning to get some changes in our values. But this is, sorry, that's column shear, I apologize. In fact, that can only be considered if we are doing an integrated design of our connections. There isn't the ability to put an additional axial in the connection, so we don't have that consideration. So the shear capacity then, the column web shear is again ever so slightly changed, and the change is really we're taking 0.9 of the square over the square root for our modification factor on shear. To the BS it was I think 0.6, but 0.9 times the square, divided by the square root of 3 gives us a factor of 0.52. So that's around about a 12% reduction again in our web shear capacity. So once we've derived all these, we look at all the potentials and we find out from all the different values what is the compression we can resist, and then we modify back, get our bolt forces, and find our balanced section. Shear design is pretty straightforward. It is similar to the simple connections. There are one or two little weird calculations involved for alpha B's and stuff like that, and K ones for getting your bearing lengths and capacity. But in the end, it comes out pretty similar. The only problem you have is when you are relying on some of your tension bolts that weren't fully loaded to give you additional resistance. In the BS, we took the applied tension over the capacity plus the applied shear over the capacity and had a 1.4 unity value on the combined. Well, in the EuroCode, the 1.4 is dragged inside the left-hand side of the formula, so it's only the tension that has a 1.4 on. That does modify the overall value to 0.28 instead of 0.4, and thus you have a 20 or 30% nearly reduction in a capacity of tension bolts, which is a pretty nice one. Welds, there's no significant changes to the welds except when we come to this sharp end of the haunch. In here, it's pretty much insisting that you have to design this a lot more rigorously. It will take the moment at the end of the haunch and divide it by the depth, work out the force, and only 50% of it can be put into the haunch. So do need to have substantial weld here compared to what we used to have. But as I was saying earlier, if we give ourselves an end of haunch moment, then we get the saving we need. So that is the most complicated joint, the beam splits, or the Eaves connection. A lot of different changes. I do have a blog document that we have written but haven't posted yet that discusses these changes. So this will be put up hopefully soon once we've reviewed it and are happy that we haven't got any spelling mistakes or mathematical mistakes in it. So we will hopefully see those. The next connection I'd like to look at is your base plate, because that's the next one that has a significant modification over what happened in the BS. So what I'm going to do is I'm going to go back to one of my calcs. So I'm just looking at my notes here for a second. And I'm going to come in, I'm going to go back and find myself my base plate. There are some differences, most definitely, between the base plate in the BS and the EuroCode. One of the most significant ones is obviously that we're dealing with this FCDs and things like that we never had in the BS. So I'm just trying to find my notes on base plates. Whoever wrote this wrote it back to front, and that was probably me. Yes. So let's looking down. The first thing is we design using a T-stub, very similar to the Eaves and Apex. And this T-stub means that for the plates, the steel, we can actually get a better design because we're using all those yield line patterns in, I believe, double curvature bending. But where we fail is in the concrete strength. Yes, we're using FCD and it's times its normal alpha over gamma C, which gives us an 11.33 Newton per millimeter squared capacity. But we then have the bearing stress, which is FJD times BJ. Now FJD, so BJ is the basically the I think the BJ is the, let me think quick, Tommy. It's the grout ratio. And the grout ratio is never really changing, but where we can get is this alpha ratio changing of 1.5. And the alpha ratio is really to do, that's right, the grout ratio is BJ. The alpha is the pad diffusion ratio. And what's happening is that, well, if we have quite a deep pad so that we're coming down through it before the concrete is no longer there, then we can increase our bearing strength because the crushed material can't go anywhere and can't even start to crush. So the EuroCode in concrete gives us this lovely interaction formula for working out a pad diffusion ratio. Now, the pad diffusion ratio really depends on the information we give it, and we need to tell it what the depth of the section is. So if I can say my base is 500 deep and 0, it's coming up with a pad diffusion ratio of 1, which is worse than the default. Not very nice. But if I then tell it that the edge distance out to the edge is 500, then we start to see a value that's starting to climb 1.85. So we're now jumping from our 11.3 to our 14 newtons per millimeter squared. So by putting in the edge distance from the edge of the bolts and from the edge of the compression zone, so in your case probably just take the edge of the plate itself, so I'm assuming 500 outside that to the edge of the concrete and 500 deep, then you can start to get a considerable increase in strength. So if I increase that to 1500, we're hitting this 1.85 still, but if I increase this to 1500, I'm now up to a pad diffusion ratio of 3. So that's an enormous improvement in my base plate bearing capacity. because I can now take 22.7 newtons per millimeter squared onto this base. So I'm going to go back to a more average 500 and 500 deep pads or 450 deep pads and come on down through the design. So that's very simple. The way it designs the base is, as I say, based on this T-stub, and since I don't have any tension zones, it's pretty straightforward. It's coming through with a compression only zone and working out what the projection is, and we're getting our effective area. If I was to come along and start to put some moments onto this, I'll say 50, we can see our centroid moving off. If I made it 150, we can see that we have a compression here and we have tension bolt here. So we're now starting to fail, and you'll see now that we're using some pretty interesting calculations to find our centroids and our moment equilibrium to find our joint. So the compression bending is very straightforward. It's a very simple formula against the bending capacity of the plate. The tension is the more complicated, where we deal with the, just like in the Eaves and apex, your upper and lower yield line patterns for the circular and individual patterns designing. Washer embedment is no different to previous. The shear design is just using the newer formulas, but again no different from previous. And the punching shear. Punching shear uses a slightly larger value of 2D rather than 1.5D for the perimeter, which gives us 4s in here rather than 3s. That's a great bonus. Well, actually that one's 4 because it's a square, but certainly that was 3 previously, so that gives us a wee bit of improvement. Where we come into some more EuroCode playing around is in the shear. Obviously the friction is very similar, the bolt shear capacity is very similar. The plate bearing is again assuming your bearing capacity on FCD min. Now the interesting thing here is that we must use the weaker of the grout and the concrete strengths, whereas previously up above we were actually allowed to use the stronger of the two, provided the grout was within a certain zone. And also here, because this is a horizontal bearing, we're not allowed to use that enhancement either. So we've got a detrimental effect on our bearing capacity of our bolts. So yes, bolt bearing has failed, has been reduced the capacity. The welds are very similar to previous with no real changes. So what I want to do now is I want to go and do some more design, but this time I want to introduce you very quickly in the last 10 minutes before I look at some of the questions. I want to look at integrated design. So if I take myself a little portal that I did there about 10 to 1 today, and I have sized it up roughly, so the sections are pretty sized, pretty well sized, if not perfect ratios. And I go into design, and I go into my connection design. Okay, we start with a joint, and I do believe I just need to link that. I actually want to delete that one. Actually, let's come back out again. 1 second, I apologize. Say no. And before I goes in, I want to delete my connections. So I'll have no connection brief whatsoever, hopefully. Connection design. It's going to tell me how do you want to do all this, and these are all settings that we can play around with to give us some guidance in our design. And I am going to first of all do my typical Eaves. Yeah, let's go for one. Now, it's asked me where, and I just pick on the rafter somewhere down near the bottom, and it pulls out, and obviously I've got quite a long haunch. I don't need to draw that whole haunch, so just turn that off. That looks a wee bit more respectable. Quite narrow 140 beams coming on to 165, so it's quite tight. But the first thing is geometry, bolts. Move that up to 90 and it now fits, but we're failing miserably. Let's get some more bolts in and let's get some compression in here very quickly. Bottom, and now let's put some more bolts in, and we go 90 and 90 and done. And as I said, that is the first of, in this case, 2 loading cases, because I didn't bother with wind analysis on this. I was just trying to get some basic simple stuff. It works. But if I reset that joint, I can come in here very quickly and say make this 90, and then say, well, why don't you design it for me? And I'll say based on 90 pitch, 10 mil stiffeners, go off and design it for me, and it gives me the same results. It even puts these down to more realistic. Now it does keep to this basic rule, but what you'll see is that we have dragged in the end of haunch force, so we could take this force or this weld and reduce it right down. So the rafter weld, haunch end weld of 20, we could try making it a 10 mil weld, and it is happy. Oh, what about an 8? No, it's not. That was a good guess. So that's my first joint designed. Let's add another joint, and we will do the same base plate type design again, but this time we'll do it on a little column, and we will see when we come in, we'll just set our grout and our concrete and just say auto design, and it will fire it up to be a standard base plate, in this case on a standard arrangement. Add another joint, and in this case we're going to add in one you haven't seen yet other than just the previews, and I'm going to do a beam to column fin plate, and I'm going to choose this member, and we will see that we actually have a problem with the welds. The BS welds are not quite as good as the Euro welds. The Euro welds aren't quite as good here as the BS welds. They're very pernickety about the weld sizes. So I went 6. If I went 8, we need an 8 mil weld, and it now works. So that is our simple integrated design coming through, and obviously in the simple connections it is only one type of connection, only one loading case. We do have our tie forces, 75 kilonewtons, but not less than. In this case, this frame, he's elected to use 25% of the shear loads. So he's taking 25% of 325, and he's turning around and saying that he has to design his structural integrity to resist those values. So the structural integrity bearing is 143, which is just about okay. So we're happy enough there in that design. So it's actually not telling us what that is. 25% is about 75 kilonewtons, which is roughly the same as that. Oh, we're okay, we're about the same value anyway, that doesn't matter. So that is a brief review of what we can do, the types of connections, the differences between the BS and the EuroCode, and how flexible and powerful the connection design program is. What I want to do now is just to look over the questions, see if there's any that need to be clarified.